Hi, this is the end of the big review of hypothesis testing. So today we're going to go beyond the single mean t-test, which we practiced on Wednesday. Today we are going to start talking about how to expand that to more useful, or not that that one isn't, it is, but it's just, it only fits one situation. So let's remind ourselves. So this is a slide I showed you already when we first started this chapter 6 Odyssey. And I was just telling you, after you see a positive exploratory data analysis, a graph, right? So EDA is what we use as the general term to refer to all charts and graphs, frequency tables, relative frequency tables, and even those summary statistics you did in task 2 part 1. So we can use anything that we see as a positive sign, a signal of something to support an idea that we're referring to as a postulate. So that's the general term for a question, a strategy, a hypothesis, something we think possibly is going on with this data. And then what we want to do is we want to check if the result can be inferred on the population. So this is what I keep telling you, that a lot of companies, a lot of people, businesses will stop and use the results from their data that they've done this charts on and graphs, and they think that that's it, that means they can make a decision on that. And what I'm trying to teach you with this hypothesis testing stuff is that's the beginning of the story. It's the middle, if you will. It's not the end, because you want to find out if you can actually infer it beyond the sample to the whole population. Because we want to have confidence. In statistics, we can't prove definitively, but we can have confidence in making correct decisions. Okay. So we already went over all this stuff about alpha. I think you guys probably, this is like beating a dead horse to death. Anyway, so alpha is our risk, right? That's the probability of being wrong. And by being wrong, we mean rejecting a true null hypothesis. So I want to go through several examples to sort of put everything in context with what we were doing with the single mean t-test. And hopefully you're making the connections and generalizations of the concepts. So in this one, this is all data from the organic food superstore. So I'm hoping it will feel more connected to the next assignment, which will be to do hypothesis testing. And I realize that details on that assignment haven't come out yet, but it's going to start with the positive postulates that you're working on for Sunday night. All right, so in this one, the exploratory data analysis is just the average income, and it's coming from the income data in the organic food superstores, the ARDS, the analysis rating data set, and it's $121,965.03. And so the question that this raised for me is the average income of the organic food superstore customers, mu, greater? And then I should have fixed the grammar there. I should take that is out. Greater than the national average of 71,000. Okay, so that's like the first thing, that first question. And I realize you guys are kind of doing it backwards, right? You're coming up with questions and then you're checking them, which is the more normal way to do this. Perhaps I should have set this up that way, but okay. Either way, you have a question and you have a signal in some sense. The second one is a proportion. So this is coming from a relative frequency table. Again, we refer to that as, in the more general term, an EDA, and we're seeing a signal here. And this is a little bit of a cartoon example, because I'm claiming that the marketing department is saying that that at least 35% of the customers at organic food superstores are coming from the online advertising, which is captured here in the category web. So we see 32%, which is less than 35%. So the question is, maybe they're not, it's not as strong as they're claiming. So we're going to ask, is that possibly, is what we're, before we go in all high and mighty and say, hey, it's not 35%, it's only 32%. We want to find out if statistically we can have confidence in that claim. So we're going to ask that question. Is the proportion of customers obtained by online ads row? So is the real row, and this, remember, this 32% is our sample proportion. So it's referred to with a P bar, right? And this is, I believe we're at 183 records in our clean data versus we're going to assume that organic food superstores has like over 10,000 customers. Okay, because they're an online chain is the idea. Okay, the next question is we look at, and this is a type of pivot table that you can do. And I probably should quickly show you how to do it. So let me do that. So if you recall, if you by any chance looked at the videos I did for the task 2 part 2, I talked about creating a whole a pivot table worksheet. And so this is sex and average spending. So the way I would set this up is, let's go to the field list, and I'm going to get rid of the race, put sex in the rows. And then the only thing that I need to do is put the spending in the sum of counts. Sum of values, excuse me. Now, a lot of people mess this up because they stop right here, and that is really useless. Don't stop with just the sum, right? We need to come down, hit that drop down value field settings, and switch this to average. So this is how I got the average of spending 2021, and of course this is money, so I can format that, copy it, and put it into a nice table somewhere. So keep my pivot table sort of like my calculator, right? It's going to do the work, but it's not where I store things. So let me add another worksheet here, and we'll call this one example 3. Okay, so on example 3, let me grab that pivot table. So I'm going to copy and paste it with special, right? Paste special. Oops, did I forget it? Yeah, sorry. Excel doesn't have a good memory buffer thingy. We always have to do it right away. Okay, there we go. All right, so let's rename this sex. And put that little table around the whole thing. And maybe just, maybe also separate out the grand total. And center everything. I like it centered better. Make this money. And I personally like currency over the accounting because if not, I don't know, makes it too big or something. But you can do what you want. It's not right or wrong. All right, I'm just make that bigger. Okay, so here we go. Now we've captured what we're seeing in my slide. All right. So in this situation, we're talking about a difference between two means, right? So the question is, we're seeing a difference between how much the female average spending is and the male. And that leads to the question, is the average spending in 2021 different between male and female customers? Now you may say, well, why did you say different and you didn't say, do females spend more than males? And that would have been fine too. I just wanted to do one of these with the word different in it. So, but it would have been totally intelligent and correct to set it up based on the signal and the inequality, the idea, the question in the direction that I see the signal. So, our female OFS customers spending more on average than male OFS customers would have been also an adequate question. But what I want you to see is the beginning of the setup of how we're going to test this. So it's really important to understand that you're going to create two subpopulations. And by the way, if you have a different variable like satisfaction or channel or membership where there's more than two categories, you still want to set this up because I'm not teaching you more than two mean differences. So you're going to pick like satisfaction, you could pick very satisfied, and the other one could be neutral. You know, is there a difference between people who are very satisfied and neutral? So you end up picking two subpopulations. You can also go with the approach um, like let's say TV is one of the channels, TV versus not TV. So that's kind of the dummy variable approach where you'd say, okay, those are my two populations, customers acquired through TV advertising or everything else. So that's kind of the way you create two subpopulations, but you want to create two subpopulations in which, and this is key because the math won't work otherwise, it won't make any sense. You're going to be measuring the exact same thing in each of the subpopulations so you can compare them to each other. So you're going to state what each subpopulation is, and then you state the parameter with a sub 1 and the parameter with a sub 2, and it has the exact same words. It is describing the exact same thing. The only difference is one is done in subpopulation 1 and one is done in subpopulation 2. Sorry, the second one's done in subpopulation 2. Okay? All right, so going back here to my, get my little annotation up. Going back here, this is my new one. Sorry, this is not my new one. This is going to be my X bar one. We'll get there actually. Right. Example 4, I have this exploratory data analysis that I did, and I was looking at the distribution of satisfaction given membership. Now, if you like this one and you want to use it, there's more here than the one I'm finding. I'm just spotting one of them. And the one I'm spotting is I looked at the gold customers and the bar for very satisfied. So that gives me this 25% right here. So I looked at this 25%, and I'm looking over here at the bronze because again, I want only two groups. I'm not teaching you the more advanced 3-group approach. We're starting simple. We're going to start with 2 groups, and that's going to be already very powerful if you can learn how to do this. Okay, so I'm comparing that to the same thing here. So I'm saying, oh, look, check it out. Gold customers appear to have a different level of very satisfied than bronze. And of course, if you are a stakeholder in any way with organic food superstores, you want everybody to be very satisfied. So that leads me to that question. Do gold customers have a higher proportion of very satisfied than bronze customers? And so there are my two subpopulations. And this is a good example of how there's a category with 3, but I have to create 2 somehow. And I could have created a dummy variable called gold membership 10, right? And said, okay, that's how I'm going to figure out who's gold, and then lump these together and this be everybody else. So it is possible, especially if you have low numbers, because in statistics, remember the sample size is everything. We want as large of numbers as possible. We don't really want to run statistics on low numbers. And I'm going to show you here in a few slides where we look at the actual numbers behind these proportions. So remember, that comes from the frequency values in the contingency table versus the converting it to our proportions. Okay. Anyway, for right now, we're just exploring. So in the way this is set up, we're saying, okay, we're going to label row 1 and row 2. We're going to look at the same thing in each bar, right? It's the proportion of very satisfied in population 1. Row 2 is the proportion of very satisfied in population 2. So remember, this is not row 1 and this is not row 2. This is a sample. It's like throwing a dart at a dartboard we don't know. This is like the bullseye. We don't know if 25% is the truth. This is what our sample claims, right? And same thing with the bronze, a different dartboard. We don't know, again, what row 2 is for that subpopulation, but we have a sample estimate, which we're going to refer to as, this one is P bar 1 and this one is P bar 2. All right, so that's going to be our 4 examples that we are going to go through. And these are the steps that are done over and over again. And these are the steps you already did with the work we did practicing this with the single mean t-test, and we've gone over the whole logic of why this is the approach for hypothesis testing over the past 2 weeks. So first of all, step 0, identify what kind of test is needed. So let's go that. I'm going to go through each one of these steps with all 4 examples. I thought about setting up this lecture by doing all technically 6 steps, 1 example at a time, but I actually think it might help to go through all 4 examples, each step, go through each step and then go and show it in each of the examples. All right, so the first thing, identify what kind of test is needed. So I put together this flow chart. If you have data, you're going to decide if it's numerical or categorical. And then you want to know how many samples you have. So let's start with going down the numerical side. If it's 1, so you're testing a claim about a population, and you know the standard deviation sigma, then it's a 1 mean z-test. And this is the one I told you is kind of, we covered this one. This is the one that I said is rare for this to happen. Occasionally, you know the sigma, the population standard deviation. Usually you don't, but this is the sort of the learning situation. And then we up it a little more messy, is you don't, right? So now you don't. Now you can't use the normal, right? The 1 mean z-test refers to a normal, standard normal distribution. Okay, we can't use that anymore. So we are now going to use a 1 mean t-test. All right, so that's the one that we've been working on, using the sample standard deviation as the S, right, replaces the sigma, because we don't know sigma. We're going to use our sample. All right, so that's where we've been. Now what happens, and if you notice, we've only come down 1 branch on this flow chart, all right? But once you know how to get there, all the way to the decision on your hypothesis, it's the same structure in all of these. So I hope to take the scariness out of it. We just have to figure out where you are and what path to take. Okay, so if you have 2 groups, 2 populations, or eventually actually 2 means you're wanting to compare, you're going to have 2 situations. There's the independent samples. So it's different people, if you will, or entities. It could be plants or, animals or whatever it is. Could be trucks, I don't know, whatever. Different independent samples. And I went ahead and skipped the super rare. I didn't want to clutter up this flow chart with things that are irrelevant. But, there is this super rare case where the standard deviation in those 2 independent samples are known and equal to each other. So let's just stick with reality. They're usually unknown. And then the question is, are they thought to be equal? And actually, there's a whole different statistical test called an F-test that can answer that question. And again, in this case, I'm going to let you guys decide on your data which way you think it is, based on your sample standard deviation. So, but there is actually a way to test it. But we're going to assume that question is answered in some sense. And so then, are they, even though they're unknown, are they assumed to be equal? If the answer is yes, then we're going to do a 2 sample t-test, assuming equal variances. So hopefully this rings a bell from your 210 core class. If they're not assumed equal, then we're going to do a 2 sample t-test, assuming unequal variances. Now remember, if we square the population standard deviation, we get the population variance. That's why they're using the word variance in the name of these tests. we usually you work with a standard deviation instead of the variance because the units match the raw data. So if you're measuring pounds, the standard deviation is in units of pounds, right? And that kind of helps our brain kind of understand what we're looking at, right? The other way that we may have two samples is what's called a paired sample. And in this case, you don't have independent samples, you have dependent samples. And with the dependent samples, um, they are coming from the same entity. Um, so, for example, for us in our organic food superstore, we only have one paired sample that's possible to create, and that is if we looked at the spending in 2020 and the spending in 2021, because those are, we can get the same exact data from the same customer. So each record has those two values. And because of that, there's a different statistical test, what's called a paired t-test, where we can actually take the difference between 2021 and 2020 and decide if on average it's different than zero, if it's greater than zero or less than zero, something what we'd be interested in doing. Because um, this actually is super, super easy. Once you set it up, it's exactly like a one mean t-test um, on the difference. And it is only possible when you have the same thing measured on the same entities more than once. And we only have that for spending 2020 and spending 2021. I'm actually kind of skipping this one because if you understand everything else and you understand the one mean t-test, if you have this situation, it's truly elementary to do it. Okay, now let's go talk about the categorical um, variables. How many samples? So again, by samples, we're referring to subpopulations or groups. So if we have one, we're going to make a claim about a population, and we're going to use the z-test for proportion, right? If we have two proportions that we want to compare, we're going to do a two sample z-test for difference in proportions, right? So those are all the tests that we're going to, so step zero, we're going to figure out which test we need. So let's go through those four examples and see what each one is. Hopefully you're already putting them together in your head. So the first one, the one numerical data where we said, okay, here's this average income and is it greater than the national average? So this is, hopefully you recognize that, that's a one mean t-test because we don't know what the population standard deviation is for the income in organic food superstore customers, which I forget, what did I say, like 10,000 or something, 15,000 nationally. I think I said 10,000 a few minutes ago. All right, whatever it is, it's more than 183, which is where this average came from, but we're gonna assume we don't know that population standard deviation. Okay, that's that one. Now let's talk about that proportion where we looked at how many, my question is, okay, is this 32%, is the real row that comes from all 10,000 customers less than the marketing department claim that it's at least 35%. And remember, rho is the proportion of customers obtained by online ads. Right, so this is a proportion, and it's one proportion that we want to compare with this number that is somehow relevant to the business question at hand. So marketing department, they are making decisions thinking that they're getting at least 35% of the customers through online ads. So for this, we go back to our flow chart. It's one proportion that we want to test a claim about. And so that's going to be a z-test for proportion. All right. The next one is a difference between two means, right? So we had male and female. We looked at their average spending. And so if we go to our flow chart, it's two independent samples because the men and then women in our sample and our data are different people. And we're gonna, at least right now, assume that we don't know if their standard deviations are the same. We're gonna say they're not. So we're gonna do a 2-sample t-test, assuming unequal variances. Example 4 was the one where I was looking at the proportion of very satisfied in gold members versus the proportion of very satisfied in bronze members, and asking if they are um, if there is if they're higher in the gold. And so going back, so I already have the answer here, but hopefully you can see it on the flow chart. Categorical number of samples 2, compare proportions. So this is going to be the two sample z-test for difference proportions. All right, so the next step, that was step 0. Step 1, put question in alternative hypothesis as we were practicing, right? So this was the kind of made me nervous. I asked this question, I think, on Monday, and like very few people answered it strongly. So yeah, we always want to put what we're asking in the alternative, and then we're going to state the hypothesis and allocate the alpha, all in one tail or split between both tails. So we're going to put the question in alternative hypothesis, state the hypothesis, allocate the alpha. And just to remind you, we're going to determine if it's a left tail. This is going to how we figure out where to allocate the alpha. If it's a left-tailed, right-tailed, or two-tailed, we always do that based on the alternative hypothesis, right? So we always use this. And so I'm focusing on the alternatives in each case. And I'm looking at the inequality and seeing which way it points. So this one points left, right? So this is left tail. This one points right. So it's right-tailed. And if it's an inequality, it's two-tailed. So that means when I draw my little normal distribution, and if it's going to be a left tail test, I'm going to find some test statistic, and this is Z. It could be a T. So, this is often a T for us. Could be a T instead. Not always a Z. All right, could be T. Don't get confused by that. This is just referring to the test statistic. But the thing is, where is the alpha? So the alpha is on the left side for a left tail test. The alpha is on the right for a right tail test. And it's split in half and allocated to each tail if it's a two-tail test. One just note, because I feel like I've talked about this for 2 weeks now, that the equality is always in the null hypothesis, right? The inequality, the strict inequality, is always in the alternative. And by strict, that means there's no equal here. Oops, let me clear my. All right, so going back to setting it up. All right, so is the average income of OFS customers be greater than the national average? So notice that question is here in the alternative. So is the mu, so when we drop the question mark and make it a statement, because we're hoping to accept it as fact or confident, not fact, but with confidence, we want to accept it. So is mu greater than 71,000? And that's going to cause us to write what the null is. The null is the mathematical opposite. So remember, either the population, either the average income of OFS customers is greater than 71,000, or it's less than or equal to. Okay, that's just logic. It has to be one or the other. So we just set that up. And then I'm going through these examples and I'm setting the significance level. So we're going to simulate or pretend that on the side we have meetings with Catherine Hill and company, and our alphas are agreed upon. So this is, there's a little bit the fake part of what we're doing here with the simulation. We're going to set an alpha, and an alpha is the risk of being wrong. So in this case, I set the alpha kind of high. Usually don't set it much higher than 20% ever. And that's really rare. Sometimes you set it much lower than 10%. But in this case, if it's higher than the national average, it's not, in my mind, I guess the way I'm thinking about the simulation is that's not going to make or break if that's wrong. It's just to give us a read on if that's possible. But the really important thing is I need to use the alternative to decide that it's a right tail test. Okay. The next one is the second one. And so the question is the proportion of customers obtain, right? Okay, we know all this. So the question, then that means that question is going to go into the alternative. So is it less? Is it actually less than 0.35? And then again, once again, that's going to force what the null is. And remember this is this important number right here. And we're going to be using this number. But is rho greater than or equal to 0.35 is our null hypothesis. This is a two sample t-test. We did this. We already figured out this unequal variances, but now we're going to set a significance level of 5%. Probably the most common alpha is 5%. You see that a lot. And the reason we want to set it a little lower like this is because if we actually can, if this is true to a 5% significance level, that could really change some decisions that are made on how much money is spent on marketing online. Right. And again, the next thing that matters is that we look here and we say, oh, this is a left tail test because the inequality points to the left. And you can always view this as like a little arrow, right? It points to the left. All right, so that's that one. Let's move on to the next one. In this one, we're looking at the average spending between males and females. We already set up the two populations. We identified what the parameter is in each population. And so then now it's just a matter of setting up the question as a mathematical inequality. So is the average spending in 2021 different between male and female customers? So that's what that question becomes my alternative. Oops. Okay. So that question is the alternative, and it's going to force the mathematical logical opposite. If they're not different, then they have to be the same. They have to be one or the other. And so here the significance is 10%. It is a two-tailed test, right? So the inequality tells us it's a two-tailed test. And then the last one, oh, I did also want to point out that what we do is we subtract what's on the right from both sides. So it's mu1 minus mu sub 2. And so we can write the equivalent version of this hypothesis. So this one the original version captures our thinking, but then we do this transformation where we're subtracting mu2 from both sides. And the reason we do that is now we've set it up as a difference in means, and we have that number here that I keep telling you becomes important. So this is our expected difference in the means in the null. We're expecting that there is no difference in the means. So in the alternative, we expect that the difference in the means is that there is a difference, and that it's not zero. Okay, again, in this one, we're going to go with an alpha of 10%, two-tailed, we already talked about that. So now let's talk about the proportion. So once again, we wanted to ask our question. So we put it, we want to know if the gold is higher, right? So we already figured out. And so we want to know if the row 1 is greater than row 2. Is the proportion of very satisfied in the gold members greater than the proportion of very satisfied in the bronze members? So we're here, and then we do the mathematical logical opposite to be the null. And we're going to set the alpha at 10%. And maybe you would argue that one really should be 5%. You could put whatever percent I encourage you to not always pick the exact same one, just because that way you're mind is thinking about what alpha means a little more deeply, which will help you, in the short run, that doesn't matter so much for the exam, but in the long run is to really understand it, right? And of course, this is a right hand test. And then we're going to do the same thing again. We're going to rewrite the way this looks so that we're going to subtract row 2 from both sides of the inequality. You guys hopefully remember how to do math with inequalities. As long as we're not dividing by a negative, it's the same as if it was an equality, right? Or multiplying by a negative. In this case, we're not. We're just subtracting a number. So we're going to subtract it, and now we have a difference in proportions, and that's why these tests go by the name difference. So the last one was a difference in means. It's a difference between two proportions. And in this case, if row 1 is greater than row 2, the difference is greater than 0. And if the null is right and it's actually less than or equal to, then the difference is less than or equal to 0. And again, what we wanted, part of the reason is in math, and statistics is sort of a subset of math, we always take a more complicated situation and then we make it look like a simple situation where we already know how to do it. So by doing this now, it looks like a single proportion mathematically. It's a number, a parameter that we don't know, right? A difference between these two. It's less than or equal to a number, and then the structure follows along with what we did for single proportion. Right. Okay. So let's go on to see what the next step is. So that we set up the hypotheses for all 4 examples. So now let's go and see what, oh yeah, this is the one I was going to do. I meant to delete this. Sorry. Okay. The step 2 is depending on which test is being done, we're going to calculate the standard error, and we're going to check the conditions for use and calculate the test statistic. And usually you do that the other way around. You want to check the conditions for use, then calculate the standard error, and then calculate the test statistic. So the test statistic, I've been telling you over and over, it always has this exact form: the observed value minus the expected value divided by the standard error. So here's that same mathematical kind of structure for a test statistic. To the observed value, the expected value is that position that comes from the null, the mu naught in the single mean t-test. 0 is when we're looking at the difference, and I should probably tell you guys that someone had suggested, well, what about looking at, is the average spending in one subpopulation double what it would be in another? And there's sometimes ways where you can make a hypothesis about the difference, and this is not 0, and that's perfectly okay. It's just usually the question is there a difference between the groups, or is one greater than the other, without having an actual number you're testing against? Okay, that's just a side comment. So that value comes from the null. So this is what we are used to seeing. So this is the single mean test. So we have the mean, the single mean z-test. Sorry, we have this actually is the same structure for the single mean z-test or the t-test. We have the sample mean minus the mu naught, and we divide by the standard error. When it's a proportion, you may remember from your 210 course, you're going to get the sample proportion, and you want to subtract off the row naught. So this again comes from the null hypothesis from that same location. This is where the number comes from every time. That's why I put up here expected value from the null hypothesis, divide by the standard error. Or with 2 samples, we have that difference in means, right? That's the observed value. So the observed value here, when it is 2 samples, is going to be the difference in the sample means. Notice the sample mean 1. Oh, that should be a 1. 1 and minus sample mean 2. I'll fix these before I put it on top hat. Hopefully I remember to do. Okay, so sample mean 1 minus sample mean 2. The difference between those minus the 0 from the expected value when we wrote the null hypothesis. And for the the difference in proportion z-test that we're going to do, we're going to get the proportion from the sample proportion we see in one set or one group, subpopulation, the sample proportion in the other group, and the value 0 coming from that null hypothesis because of how we set it up. And then we're going to divide by the standard error. All right. Then that's just a little review on how we always get the same structure for the test statistic. What we're going to want to know are what are their conditions for use. So if it's a one mean z-test, if the n is less than 30, x has to be normally distributed. If it's greater than or equal to 30, there can be no outliers. Otherwise, we have to run the sensitivity analysis. And those same rules pretty much apply for the one mean t-test. The only difference is that with the one mean t-test, we also need to calculate the degrees of freedom because that's a family of distributions, not just one. And which one it is depends on the sample size, n, and we subtract 1 off for the degrees of freedom. In the situation where we are considering two independent samples, we are going to do these different tests, and the degrees of freedom are different depending on which one you're doing. So if you are assuming equal variances, the degrees of freedom is the sum of the sample sizes minus 2. So it's really n minus 1 plus n minus 1, 1 for each one, so you get n1 plus n2 minus 2. If we're going to assume unequal variances, then the degrees of freedom are this weird, giant, crazy fraction, which is called Welch's degrees of freedom. So if we are doing proportion, we have some conditions for use. We have to make sure a single proportion we have greater than or equal to 30 sample size, and that sample size times the sample proportion is greater than or equal to 5, and the sample size times 1 minus that proportion is greater than or equal to 5. Right. And then if it's a two sample z-test for difference in proportions, we need the product of each one times the sample proportion to be greater than or equal to 5. Okay. So, and then we have to calculate the standard errors, which are going to be different depending on which test you're on. So we've already talked about the standard error for a one mean z-test. This is the one you've been working with, that we worked with together in class on Wednesday. Right, so now, if we are in this more messy scenario, it's still a standard error. It still goes in the same place in the test statistic. It just has a much more complicated structure. So a two sample t-test assuming equal variances has this pooled, that's what the little p stands for, a pooled estimate of the overall equal, right? This is the situation where we're trying to make an estimate of the sigma where these are equal. So we pool the information in this weighted average approach to obtaining the standard error. If they're not assumed equal, the standard error then is a more direct weighted average approach that's used. Okay. For the proportion, the standard error has this form, and the structure for this form is beyond the scope of what I'm covering. You could certainly understand it. It's just a little complicated, and we're going to skip it. Okay. So you have to trust me and all the rest of the world that does statistics that this is what it is. And for a two sample z-test for a difference in proportions, we again have this sort of weighted term, which is referred to as PP, and and that's included as a factor in this more complicated structure of the standard error, where we're multiplying this, what we get out of this, and we're calling PP, whatever that number is, multiply that by 1 time minus that same number, and then multiply that by 1 over n1 plus 1 over n2. Okay, so let's go through this for each one of those examples. So the first example, we're going to be here in the single mean. So we set it all up, and the degrees of freedom are the n minus 1, or 182, because we had a sample size of 183. We already recognize it was a student's t-test, and so because it's a student's t-test, we know that our standard error is going to be s divided by the square root of 183. And our test statistic, which we're going to calculate, is always going to have the expected value, the sample mean, x bar, minus the mu naught, right? This is our mu naught position. We've been talking about that position being the number that gets pulled into, whatever number is here is what gets pulled into this position when we calculate the test statistic. And then we divide by the standard error every time. All right, so for us, we have that sample mean, that was part of our EDA, and you could also calculate the sample standard deviation. So remember in Excel, the function for that, it was back in the slides from chapter 3, but it's standard dev.s because it's a sample. We put all these numbers together and we end up with 15.1786. And this is the setup for running the test. Okay. Oops. Got moved a little. Now let's look at the second one. The second one was a single proportion. And so that is the test statistic has the same form. In this case, we are going to check, we're going to check our conditions for use, which was if n is greater than or equal to 30, which we are fine because we know already that we have a sample size of 183 and we have clean data. So it's true, not only is it true over here for the income variable, but it's also true over here for the channel variable. So that's true, and our proportion, so this n is the overall sample size, not the number that had the online advertising as the way that that customer was obtained. So it's not the subset. You're not looking at the number that had web down as their channel. You're looking at the number in the entire column for channel, right? And the proportion is the number that had web divided by 183, right? So that's the proportion. That gives us this 0.3224, roughly 32%. We need to multiply these two together. That's roughly a third. So a third of 30 is 10. So I'm good here. I'm kind of doing that in my head. And then if the proportion is around 30%, 1 minus, or what's left, is 2/3. And, if a third times our sample size is greater than 10, then 2/3 is also greater than or equal to 5. So we're good on both of these. You can do the math on the Organic Food Superstore if you don't believe me. Okay, the standard error is calculated using this number, the rho naught, right? So the number that's here is always referred to in terms of the parameter of interest, and we usually give it a little knot referring to the null hypothesis. Right, so that number is the one that always goes in this position when you're calculating a test statistic. Right, so that number is here. And then this is coming from our sample. right? So that's this sample. So again, going back to the same structure over and over again. Once you get it, you're like, okay, I get it. But sorry, we got to go through it. All right. So standard error is calculated with this funky square root rho naught times 1 minus rho naught over n. Putting it all in, we get 0.0353. That's always in our denominator. And we end up with a test statistic of negative 0.7828. Okay, so we did all this. That's our getting, that's our setup. So let's go into the third one. And we had said this is a two-sample t-test assuming unequal variances. And I highlighted in yellow here that it's important to understand that this can be done in Excel. So it looked really, really complicated, right, in our flow chart. So go back to that scary stuff. We're here for our degrees of freedom, and I think that's where we are. Yeah. And the standard error formula, right? So it's not as complicated as this one over here. This one, unfortunately, there's nothing in Excel to help us. But for this one, the two sample t-test assuming equal variances, and this one, the two independent samples t-test ones are programmed in Excel. And so is the paired t-test. So I'll show you guys that in a minute. All right, so it's the same setup. We're going to get our sample means from each subpopulation. So we have it right here, right? So this is where oops, my bad. I was trying to show you before I started before. This is our X bar 1, and this is our X bar, right? Oh, did I get that backwards? Sorry. Females are subpopulation 2 for some reason. I split it. 2, and this is X bar 1. I think I might, yeah. Oh, it did not equal to good. Okay. I thought I flipped my inequality. All right. You got to keep it straight, right? So I should have switched my pivot table to match the way I wrote this. I made subpopulation males 1. It kind of really would have been a little better if I had made that my top row. All right. In case you're wondering how to do that, let me just show you. So, oops. In the pivot table, I think this is in a couple videos, but I could grab this, select not the whole row, not the row from the 5, just the male, and hover around it because that's a label for this row. Hover around until I get this 4-pointed arrow thing, and then just drag it up, and that switches the order. So this would be a better version than what I have in my slides. So again, I will try to fix that before I upload to Top Hat. Okay. Oh, okay. So the last one was a difference between two proportions, and we were talking about the gold customers versus the bronze customers. And the question is the proportion that's very satisfied grade. So we said, okay, it's a two sample Z test for a difference in proportions. So all this comes from previous slides. So now we got to check, is N1 times P1 bar greater than or equal to 5, and is N2 times P bar 2 greater than or equal to 5? So I'm going to be looking at the N1 equals 20 is coming from here, right? Actually, maybe I can stick with my highlighter. Yeah, okay. So that's my N1 equals 20. And what's my P1 bar? Well, first of all, up here, this is the pivot table where I only calculated the quantities. And maybe let me pause a second and get these tables for you. So let's get these tables together. So again, we're doing membership and satisfaction. So going back to my pivot table, I'm going to get rid of sex, get membership as my rows, and I'm going to get satisfaction as my columns. And I'm going to get rid of average spending here. That's how you would do a heat map, by the way. You have two categorical, one numerical. But I'm going to switch that out and I'm just going to drag down satisfaction just to get the counts. And these are not dollars anymore. So let me just switch this back over to general. Okay. Notice it goes neutral, somewhat satisfied, very dissatisfied, very satisfied. So it's doing them in alphabetical. It ordered them in alphabetical. So I don't like that order. So I'm going to get very dissatisfied. I'm going to get that four-pointed arrow, drag it over, and I'm going to get somewhat dissatisfied and do the same thing. That way it goes from, it's an ordinal categorical variable. It has an order to it. So it's very dissatisfied, somewhat dissatisfied, neutral, somewhat satisfied, and very satisfied. And then we have another ordinal variable. We have memberships levels. And we set these up, if you recall, based on spending. So we know they have an order and it should go gold, silver, and then bronze. So bronze should be at the bottom. So I'm going to grab that one and drag it down. Oops. Sometimes Excel is picky. So let's try that again. You should have the solid green bar if you kind of on the right track with it. All right. So this was example 4. So let me create down here another worksheet. We're going to call this one example 4. And let's put these pivot tables in here. So we're going to start in here by having the EDA. And let's get this pivot table here. So this is going to be our counts. We're going to need this as I just showed you on the slide. This is part of the setup. Oh, my mistake. We actually want to put this in with paste special values. All right, so this is going to be, I'm going to format this real quick. So these are my levels of satisfaction. This is, and delete that, and this is my membership here. Okay. I'm not going to have specific things I'm looking for in how you format tables, as long as they look professional, look nice. And you have things, at least the membership added here to, if you're doing a contingency table like this, because that's normally, that wasn't there. And it's important information. Whether you do this merge and center stuff and just how fancy your formatting gets is up to you. I do expect it to look a little bit professional, but it doesn't, it's not, I'm not super picky there, I guess is what I'm trying to say, because there's different opinions on what one should do. So here I'm going to just quickly do these borders. I'm going to make all this bold, and the bottom one bold. Some people might feel like they want to bold those numbers too. It's up to you. You can decide how you want to do all this. I'm going to center everything. And then I'm going to make the columns a little wider, but they're still not wide enough. I don't want to make them too wide, so I'm going to actually wrap text on these. Okay, so that's what I'm doing. And you know, you can get fancy and shade, you know, whatever. I feel like a little bit like that. Maybe you want to make this bold too. Okay, whatever. You know, there's a point where you just like, okay, that's good enough for me. All right. Notice the one I put on the slide was much more simple. I was just kind of playing around. All right. So now we need to get it. Also, we need to now decide how we're going to get the proportions because these are just the counts. And so, and I did put the count, I put the count table here. We're going to need those counts because we're going to need the N1 and the N2 as part of these calculations. So you need that. So that's N1. And then the other one that I'm going to need is the N2, which is the bronze, which is over here, the 50, the total population size. Again, it's not the number that is the numerator in our proportion, it's the denominator. You need the whole sample size from over here. Okay, so let's go back to Excel and talk about why I have 100% in the right on the proportions and how to get that. Oops, it was there. Okay. So back over here, because I want to, I played around with this, you know, and I saw something, and the way I set it up was conditioned. So the technical term is conditioned on membership. I wanted to know the different proportions of satisfaction conditioned on membership. So another way of saying condition is given. So given that you have a gold member, what proportion of gold members are the different levels of satisfaction? If you want to ask that question, then we're going to have 100% in the grand total. And that means when we go to our value field settings, we go to show value as, and we go to show the calculation, we're going to choose percent of row total. That's a very different question than if you're talking about all the people that are very satisfied, what proportion are gold and what proportion are bronze. Okay, that's a different question. To do that question, we would go to value field settings and show value as percentage of column total. All right, so now the sum is down here. So of all the customers that are very satisfied, we see that 63.41 are silver, 24% of those are bronze, and 12.2% are silver, are gold. Now, the reason why that is not the right way to do this is because those proportions are also based on the total values of the quantities, and there are far fewer gold members than there are silver and bronze. So those proportions are sort of, I want to say confusing, non-informative. So you want to really be clear on what you're asking, and it does take some practice. So if you're like feeling a little sketchy about that, you have good reason to. You have to really think hard about what you're asking. All right, so let's go to show value as, and the one we want is percentage of row total, because what we want is to say something about the proportion of, given that it's gold. So I'm conditioning on the rows, conditioning on membership. All right, so now that I have this, I'm going to copy this over to my example 4, where I'm putting my EDAs here. I'm going to copy that down. I'm going to select the previous table and choose this little paintbrush. I think on Macs, you just have to get it from the home. It's always on the home screen. There's always like 3 ways to find everything in Excel. So let's I go with that. I'm going to select that, and it's going to automatically format everything, but it's not going to do this change that I did up here. So I'm going to just copy that here. All right, so that all looks good. The other problem is this is percentages now. So let's make these percents. So that's going to give us the tables that are in my slide deck. A little more formatted with this weird gray blue color, which actually I don't like, but whatever. I just want to show you stuff you could do. All right. So given that, now we're back to everything that's on this slide. And now we're going to get our sample proportions. So our sample proportion is based on the proportion of very do that. The proportion, hello, the proportion of very satisfied. All right, so the proportion of very satisfied for subpopulation 1, which is the gold numbers, is going to be gold. We come over to very satisfied, and it's this, 25%. So that's where this 0.025 comes in. We multiply those together, and we get that it's 5. Woo, right on the cusp of not being able to use this and having to come up with a different thing because we can't do it with our data. So I am not expecting you guys to know what to do. If you don't meet that condition and you still want to do the same test, what I'm telling you is go find a different test. Go set up a different postulate. Because then in the real world, you'd have to go hire a statistician to help you at that point. Everything I'm showing you right now is sort of kind of what I call layman's statistics. It's, bachelor's degree level of a business degree and exposure to stats 1, and that's what you're doing. This is 210 review still. Everything you may or may not have gone to this in 210, but either way, 210 plus a little, but not like graduate level statistics. All right. The next one, bronze. Okay, bronze, very satisfied. Remember, we got to get the exact same thing. I can't come over here and compare it to somewhat satisfied. That would make no sense. So very satisfied is 20%. So I got my 50 is my sample size for bronze. My proportion of those that are very satisfied is 20%. I multiply those together and I get 10. So I'm checking this box too. So check, sorry. So I'm checking both of these. Yep. All right. So now I know that I'm going to put it into this form. I'm going to drop that 0 because subtracting 0 is fine to put it like this. And that's the form I'm going to put in to get my test statistic. But I need to calculate the standard error. Unfortunately, Excel won't do this for you. You actually have to program this. And so let's go ahead and do that. Let me bring my Excel stuff back over here. And get rid of this. And let's go in here. And I'm just going to come in here and I'm going to say N1, or maybe P bar 1. N1. Oh, wow, look at that. It's formatting for me. Cool. Doesn't always do that. Okay. I don't know why it's doing that. Okay. P bar 1 was the 0.25. The N1 was the 20. And then P bar 2 and N2. P bar 2 was the 20%, and then N2 was 50. Okay. Alrighty. And then we have to do this complicated fraction. So the way I'm going to do it, you can do what you want, but I would recommend doing PP numerator. And just that's already complicated enough. Let's just equals P bar 1 times N1 plus P bar 2 times N2. All right, so I got that numerator. And let's get the PP denominator. And so that denominator is just N1 plus N2. So N1 plus, oops, my bad. I forgot the equal sign. Equals N1 plus N2. All right. And then we just, now that we set up the numerator and denominator, we don't have to do so much crazy stuff in Excel. We just say equals numerator divided by the denominator. And now we have our PP value here. And now we're going to have to come up with a standard error formula. So let's go here and call this the standard error. And this is going to equal the square root and I'm going to multiply PP times 1, and I got to put parentheses, 1 minus PP, close the parentheses, and multiply that by 1 divided by N1 plus 1 divided by N2. Now, the good thing about this is once you set this up, you don't have to do this again, right? You can hopefully set it up if you put everything sort of in the same place, or, kind of set it up. You can reuse this as a template, right? So now I'm going to close the square root function, which is the wrapper on the outside, and I get 0.108562. Right, so now I need to get my test statistic. And for that one, I'm going to move my Excel over to remind us that it's just P1 bar minus P2 bar divided by the standard error. It's going to equal P1 bar minus P2 bar. All right, oops, and I forgot to put parentheses around my numerator, so let me come up and do that. Parentheses. Probably by now you figured out that once you have to make any edits, you have to come up here to this formula bar line and divide that by the standard error. Okay. And we get a test statistic of 0.460566. Okay, let's keep going here. So that was step 2. You're like, wow, only made it through step 2. Yep. Now we're going to go to calculate the p-value. That'll be step 3, and that's going to be based on the distribution of the test statistic. So test statistics exist because they follow certain distributions. The ones we're talking about is the normal distribution or the t-distribution. And we're also going to care about, when we're calculating the p-value, this is really where it matters, if it's left-tailed, right-tailed, or two-tailed. Let's talk about that a little bit more based on the alternative hypothesis that I already showed you this before. And we're going to use the test statistic to determine the p-value, which is the probability of seeing the test statistic value if the null is true. So whatever's in the right-hand side in that special position is being standardized or normalized, that position gets translated to 0. And if it's a left-tailed test, then we are going to put our test statistic, the location of the null hypothesis, it gets translated to 0 here. So we're looking at a p-value of area in the left tail. Again, the normal distribution around 0, and we have a test statistic that will give us a area in the right tail, and that's what we call the p-value. And if it's a two-tailed test, whatever the value of your test statistic is, the negative version of it, if it's a negative, it goes here, or I should actually had absolute value in this too, because just, you don't have to come. All this means, this is just a mathematical way of capturing every single scenario that can happen. So you go negative value, you put the negative of the absolute value of that negative, it's going to be the negative version here, and then the positive version goes here. Either way, you have symmetry around 0, and the p-value is the sum of the area in the tails. All right. So this one is calculate the p-value using the appropriate distribution. So once again, you can go through this and determine which is the appropriate distribution. The only two we're dealing with is normal, and that's the ones we're using for the categorical proportions, or the t distribution, which is what we end up using for 1, 2, 3, 4 possibilities are all t distributions. The t-test for the 2 sample ones is in Excel. For the single mean t-test, we this is what we were working on Wednesday. We use the t-dist or the t.dist.right tail or the t.dist.two tail. And that ends up being what you use. The paired t-test just becomes the one mean t-test, so it's the same. And then this is that unlikely scenario that you know the population standard deviation, you'd use the normal distribution for a one mean z-test. So I put all this together now in these tables. So this is everything that's in the flow chart, but you just, like, you already know the name of the test that you want. And so this is all in one place. So depending on how you like to look at this information and have it accessible, I'm going to print out these tables for you. So this is numerical data, one sample, this is numerical data, two independent samples. Then I have the paired difference. So you just take the difference and you create a new variable d, the difference, and then it's just a paired t-test. It looks just like a single mean t-test. All right. Or categorical data, single proportion, difference between two proportions. So in all of these, we're going to get the p-value, and then we're going to compare it to the significance level alpha. And we've talked about this, that we're going, if the p-value, oops, that was supposed to be less than or equal to, if the p-value is less than or equal to alpha, we're going to reject the null and accept the alternative. We say the test is statistically significant. And that is, that's sort of what we're hoping to get, in a sense. It is a significant test. We go through all this because we see something in the exploratory data and we think it's a signal, and we're hoping to kind of confirm it to some confidence level. Oh, Cecilia. This was, if the p-value is not, is just strictly greater than, again, these slides will be fixed when they go on top of that. If the p-value is strictly greater than alpha, we do not reject the null. Okay, the test is not statistically significant. The data does not support rejecting the null hypothesis. So again, the p-value, if it's a left-tailed, right-tailed, or two-tailed test, comes from there. And then we are going to compare where the alpha is. So I'm not implying by this that the left-tailed tests always have the alpha bigger than the p-value. I'm just showing you in one case you could, this could have happened in any of the other scenarios as well. I think hopefully that's clear. The p-value is less than or equal to alpha, then we reject the null. Or if you have a p-value where it's greater, the area under the curve is greater than the amount of area in the tail of the error that you were willing to live with, the risk. Remember, alpha is like the risk. So this has more risk of being wrong. And so we would say, nope, we're not going to reject the null. Right. And you either think of alpha over gets divided and put in each tail when it's a two-tailed test. So you can either compare one tail to alpha over two, or you can add the two p-values together and compare the alphas, which would follow the same structure here. Probably is the better way to do it. All right, so let's go through each one of these. All right, so we got the p-value. We're back to example one. We're talking about the single mean. This is like the examples we were doing in class on Wednesday. We do a t-dist right tail because this is a right tail test. And so we can use this convenience function. We put in our t-statistic that we calculated, and we got to put in the degrees of freedom, right? Which is this. So the degrees of freedom was n-1. And that is in the flow chart. And I think we've talked about it a bunch. So that's the 183 minus 1. And what we get out of that, I highlighted this to make sure I go over this with you. Excel gives you scientific notation, and the way it formats it is it gives you the value with one number and then the decimals. It has this E, that's how you know you're getting an answer in scientific notation. And then it has a number after it. And what it means is this this E negative 34 means times 10 raised to the negative 34th power. So basically, you take this one, what this number actually is, right, is you take this decimal and you move it 34. It's a negative 34, it's 34 to the left. And so this number is like 0.000, out 33 zeros and then 18555. So it's really, really small. So it's teeny tiny area over here in this tail. So is that p-value less than or equal to alpha? Yes, absolutely. That's a tiny number. So we reject the null and we accept the alternative. And we would say that this is very strong evidence against the null because that value is so small. We feel like it's almost impossible that we would get this average in a sample if the true mean population, if the true mean income for these customers is less than or equal to 71,000. So we feel like there's a lot of evidence against the null. That's very, very strong evidence against the null. We accept the alternative. And so we could actually even, kind of increase this. I mean, we tested it to 10% significance. Some researchers and some people don't actually state the alpha. They state the p-value only as the evidence against the null. So you'd say it's very strong, evidence against the null with a p-value of 1.855 times 10 to the negative 34. But it is perfectly okay to refer back to the alpha where we set the bar before actually looking at the data. So we could say to the 10% significance, OFS customers' incomes are on average higher than the national average. And notice that I restate in that interpretation. I've accepted the alternative now, so I use that when I write my interpretation. All right, so now let's look at the single proportion. Here we're going to use the z-test, and that's what was on the, let me get back to single proportion, standard normal distribution. So we're going to use a norm S dist. And that was also in the flow chart if you prefer flow charts. So let me get back here. Okay, so here we are with our norm S dist. It's a left tail test. So we're going to put in that z statistic, and we're going to, the norm S distribution function, you have to put true for the cumulative distribution up to the negative 0.78. And that gives us this area that's in yellow highlight. That's the p-value of 0.2169, or around 22% of the area under the probability. So we're comparing that with this alpha of 5%, right? So 22% is a lot more than the 5%. So there's way more chance that if we rejected the null, we'd be wrong. So we're going to say, okay, we are only willing to be wrong 5% of the time. So because of that, we're not going to reject the null. So the interpretation is that to the 5% significance, the data does not support the claim that now because I did not reject the null, what I state here is the null written in words. Okay. To the 5% significance, the data does not support the claim that the proportion of OFS customers obtained by web advertising is less than 35%. Oh, sorry, I wrote the alternative version. You can do that as well. You just have to be careful the way you don't get into a double negative scenario. Okay. It does not support the claim that it's less than 35%. So we can't support that claim. To a 5% significance level, we cannot reject that it might actually be 35%, at least 35%. All right, let's go to the third one now. So in the third one, we're going to do this. It's a two-sided test. So we have alpha in each tail. So the alpha was 10%. So we're going to have like 5% in each tail. But we're going to do it in Excel. We're going to go to data analysis, t-test. So let me show you that in Excel. So here's where we are working on this example. 3. And we were talking about the average spending of males and females. So what we're going to do is we're going to go over to the data, and I have to create subsets of this data. So I'm going to find my variable sex, and I'm going to use the filter, and I'm going to start out with the males. And now that I have the males, I'm going to get the average spending in 2021. So I'm going to select this information. And I'm going to copy that over to example 3. And let's see, I'm going to put it right here. I could have set it up ahead of time, but let me go ahead and put it in here for right now. And I'm going to call this I'm going to call this the males. So it's all going to be spending 2021. I want to get the males and the females side by side, their data, each side by side. Okay, so now I want to get the females. So let's go back over to the ARDS data, and now I'm going to reset my filter. And this time I'm going to get the females customers. So getting the female customers, I'm going to go up here to, we don't need that label actually. I get all this data. Oops. I'm copying. Let me do that again. So you just kind of want to make sure nothing got messed up. They should be different numbers coming across, and they are, and there should be a different amount in each one. All right, so now that I've set up my 2 columns of actual sample data, I'm going to run 2 sample t-tests. And to do that, I'm going to go to data analysis. I'm going to come down towards the bottom. Remember, these are all in alphabetical order. So I want the t-test to sample, assuming unequal variances. And it was variable range 1. So that's just going to get, now this I do want the labels in here because it'll help me when I look at the output to know what I'm looking at. So I'm going to go from males, shift control or shift command and down arrow key. I'm going to get that data. And then I want to get it for variable range 2. Same thing, select females, shift control down arrow key. And then I'm going to come here to this hypothesized mean difference. And this is, oh, it's not going to let me move it. Maybe it will actually. Yeah. So the hypothesized mean difference is from the null. So that's this number right here that I've been talking about is a special position that we end up using a lot. So we're using it right now. We're going to have, and again, this could be something different than 0. That's what your hypothesis is. But because we're just starting with a simple case, are they just different from each other? When I subtracted mu2, the null becomes that they're equal. And so when I subtract mu2, I get 0 here. So I'm going to use this as my hypothesized mean difference. All right, so in here I'll put 0. And then I do have labels. And then I'm going to put my stated alpha. I don't remember now. So many examples. What should we say? Alpha is 10% here. So let's go with alpha is 10%. And I'm going to select my output range. And I'm just going to put it right next to where we've been working with this data. Then I say OK. And it's going to give me this little table of output. So for this table of output, I'm going to make this a little bit bigger so I can read what everything is. Actually, let's select these two and shrink these back down. All right. And so since we're talking about spending, I'm going to format this as currency. So everything up until here, I'll put a little underbar, is just some stats, the mean and the variance and the number of observations in each of my subpopulations. Then what's below that is the hypothesized mean difference, the degrees of freedom. So again, this is coming from this complicated calculations. And then we have the t-statistic. So the t-statistic is negative. So in our little sketch, this was a two-sided test, the way we set it up. So it's minus 3.27. Oops. And then what's going to be important is that you have to know what to look at after that. And because this is a two-tailed test, all right, we want to use the p-value associated with two-tailed. So if you had a different hypothesis setup, you would use the one-tailed p-value. Okay, so we're going to use this one. I'm going to select this and highlight this in yellow, just so we're clear on that. So that's our p-value. That's the sum of when it's a two-tailed, it's going to be the yellow, the symmetric amounts from each side. So it's whatever the p-value was from one side multiplied by 2. And you can prove that to yourself because right here is the one-sided one. But you got to know what to compare your alpha to. So our alpha is 10%. All right. And so we got to run our comparison. So we're going to, again, just like we were doing on Wednesday, is the p-value less than or equal to the alpha. And we can just set that up. We're going to say equals. And so let's go grab the p-value. And then we're going to say, is that less than or equal to the alpha? True. And so if you have this in another, I don't have that Excel file open right now, so I'm just going to reprogram it. Yeah, so equals if this is true or false. If it's true, we're going to reject the null. And if it's not, we do not reject the null. Close that. All right, so I get my answer out of this. I'm going to reject the null. All right, so putting that in here. So this is just a copy of what I was just showing you. So we accept the alternative. And so the interpretation is to a significance of 10%, there was a difference in average spending in 2021 between male and female customers. All right, so I'm stating that alternative here. All right, so what about when you're looking at the difference between two proportions? So this was a right tail test. We calculated the Z statistic. So we need to get, according to either the flow chart or the tables, wherever you want to look, we're going to use the normal distribution when we're dealing with proportions. And because it's a right tail test, we want the area under the curve to the right of 0.46, which was our test statistic. So the area under the curve to the right, you cannot get from Excel or from tables. If you remember, you have to get the area, it's 1 minus the area to the left. So this is the area to the right, right? So we're going to do 1 minus the area to the left. So we're going to get this out of the tables, which I highly recommend you do not use. Although I know some of you learned that. So we want the area to the left. So that area to the left is going to be the probability that any standard normal variable z is less than or equal to 0.46. So 1 minus the norm s dist, that number, and true will give us the red lines here I wrote. So that is 67%, 67.74% of the data is there. So 1 minus 0.6774 gives us a 0.3226, which is what's in yellow highlighted there. And so if let's go ahead and go over how I got this out of Excel. So here's our Excel, and let's go to example 4. So example 4, we had this stuff here. We have our test statistic. Now we want to get the p-value. And this is a right-tailed. You can set this up. You can set it all up so you have it for right-tailed, left-tailed, two-tailed, if you want to be that fancy. All right, p-value. So this is going to equal 1 minus the area to the left, right? Oops. And that's the norm S, because it's a standard normal distribution of that value, and then true. So we don't have anything with degrees of freedom when we're working with a standard normal. There's only one standard normal curve. So that's why we don't need to put that in here. And we get the 0.32255. We can put in the alpha. And the alpha is 10%. And then we can do our question and hypothesis again, our decision. So our hypothesis test is the p-value less than or equal to alpha. So let's decide that equals the p-value, grab it, less than or equal to alpha, false. And then so our decision, and I'm just going to copy it from example 3 because this in the same position, I can copy it here. And I can just confirm that it is pointing to the cell right above it. Nothing moved. That's good. And do not reject the null. So we come over here and we have the decision, do not reject the null hypothesis. Because the area under that curve is much larger. The p-value, the probability of being wrong, if we reject the null, is much greater than 10%. So we do not reject the null. And to a 10% significance, there's not enough evidence to reject the claim that the proportion of very satisfied gold customers is the same or less than the proportion of very satisfied customers that are bronze. You could also state it with the alternative and say to a 10% significance level, there's not enough evidence to accept the claim that very satisfied, that the proportion of very satisfied customers that are gold members is higher than very satisfied bronze members. So this is a great example where it looked like we saw something that, and you would think it makes sense, right? That that gold members, they're spending more, that they would be very satisfied. But it actually is statistically not, there's no confidence that that's an accurate statement. It's just, it could be by chance what our sample data looks like. It doesn't mean it's true. So going back to that original, let's go back to that original graph. Let me get back there because I think this is an important point. Gotta find it real quick, sorry. There it is. So it looks like we have a signal, but we showed by statistical analysis that we don't. So we would not So in other words, there does not seem to be this link that people who are spending more are necessarily claiming they're more satisfied. Maybe they've raised the bar and they're judging OFS harsher because they're spending more money there. They're expecting it to be better. I mean, I don't know what's in their mind, but whatever reason, we're not seeing, we didn't show that statistically. So, you know, I'm not going to give away what would be potentially another question that could be asked from this bar chart. But there's other questions that are here that maybe something pops out at you. All right. So with that, let me go back to where we were. Okay, so we made the decision, we compared the p-value with alpha. This is just, again, going over the decision criteria. And we restated in all four examples the decision that we made from the hypothesis test. So that's it. All right. Um, See you guys Monday.